Hello everyone, my name is Franco Pucci. I'm the technical consultant for the STS Association. Welcome to Training Video Series 2, where we will explore the companion specifications. I hope you find these videos helpful. In this video, we will look at the STS600-8-6 companion specification. In particular, the supported commands. Please refer to the relevant document for detailed descriptions, and the document number is STS600-8-6 Hardware Security Module API. So, under the commands, we have general and diagnostic commands. We have a get identification, which is an SM?DI. This command queries the HSM identifier and the firmware identifier. We have a query identification, SMQI. This command queries the HSM unique identifier, hardware identifier, firmware identifier, and firmware hash. Query date, SMQD, which queries the date and time of the real-time clocks, and it also returns the TID window. And the query log, SMQL, which receives a specific entry for the HSM's log file if it exists. By calling this function repeatedly, all log entries can be retrieved. Still under general and diagnostic, you have echo data, GLEC, which echoes back data to the HSM. It can be used to test communications. And you can also reset the device using a GLRS, which is all current activities are halted and the device is reset to a state in which it is ready to receive and process commands. Now let's look at the key management commands. List the KEX slots, SMGL. This fetches a list of KEX slot identifiers. It is typically used in conjunction with the SMKQ, which fetches information about a single KEX slot given the slot identifier. You can query the KEX slot, which fetches information about a KEX slot. To fetch information about all KEX slots, iterate over the list of slot identifiers returned by the SMGL. Then to generate a VK load request when you need more vending keys or need to replace vending keys in your security module, you use the SMKC command, which returns a VK load request given the KMC's current valid public key. Loading the VK load response, which is returned from the KMC, you use an SMKR, which loads the VK load response, and you can see section 7.4 of the STS600-4-2. And the VK load response is sent from the KMC in a keyload file. Still under key management commands, you can load a vending key, which is SMKL. You can VK loading. When VK loading is finished, you issue the SMKF command. You can delete a KEX slot and all the vending keys in the module. You can get attributes for each of the vending keys if you know the vending key number using an SMGA command, and you can delete a vending key using an SMKD command. Then under STS transfer credit commands, you have an SMVC, which constructs an STS class 0 credit token and encrypts the token under a decoder key that is derived for a specific meter from the VK. Please note that decoder keys are not stored in a security module, only the vending keys. Each time you ask for a token, you have to give the meter number anyway, and the supply group code, etc., and that will generate a decoder key on the fly and then encrypt the token according to that decoder or using that decoder key. Credit transfer commands are only available in vending secure modules with vending firmware. Manufacturing modules cannot generate credit tokens. Please also note that vending may be restricted by the vending key attributes that limit the key use. For example, a key may have expired, or you may have exceeded the vend limit of the security module, or you may run out of credit in the secure module. If the TID is a special reserved token identifier instance, please consult IEC 62055-41 for this terminology and what it is. Then the TID to RTC window has no effect. Also, please note that the secure module does not generate tokens for reserved subclasses 8 to 15. Under management commands, this is the SM VM command. This will construct an STS class 2 meter-specific management token and encrypts the token under a decoder key that is derived for a specific meter from the vending key. Subclass 0, you have set maximum power limit, and with the maximum power limit field as defined in 6.2.4 of the -41 spec, you have a clear credit, a set tariff rate, clear tamper condition, which is subclass 5, set maximum phase power unbalanced limit, subclass 6, subclass 7 is a set water meter factor, and subclass 10 is for the extended token set. And that you can find in 202-5. Management commands continue. Generate an STS key change token. That's the SMVK command. This will construct a set of key change tokens. Each token is encrypted under the decoder key. The HSM enforces several rules when generating key change tokens, and here are the key change rules. If the source VK is expired, in other words, now is greater than the issued until date, then reject the change. If the destination VK is expired, now is greater than UIT, then reject the change. If the source VK and the destination VK are from different key management centers, then reject the change. If the source VK's cluster is not 0 and is different to the destination VK's cluster, then reject the change. If the source VK's base date is greater than the destination VK's base date, then reject the change. If the source VK's base date equals the destination VK's base date, then allow the change. And if the source VK's base date is prior to the destination VK base date, then allow the change and set the rollover bit. So this last one, what that means is if you've got a base date of, say, 1993 in the source vending key, and you are going to a destination vending key base date of 2014, then the secure module knows this is a base date change and you're doing a rollover, therefore allow the change and set the rollover bit in the token at the same time. This will then allow you to do a rollover key change on that particular meter. You can also verify an encrypted token using the SMVT. This decrypts an STS token using the decoder key, verifies the token's CRC, and returns information about that token. The information returned includes the class, subclass, transfer amount, and TID value of the token. So to conclude, let's look at the manufacturing commands. Manufacturing commands are only available on security modules that have manufacturing firmware. These commands provide the functionality required by the meter manufacturers to work with the DITKs, also known as dispenser ROM keys or initialization keys. IEC 62055-41 provides for a DK that is owned and managed by the meter manufacturer. The DITK is in plain text and it's used to initialize the meter's decoder key register during production or repair at the manufacturer's premises. But please note that before leaving the manufacturer's premises, no meter must leave with a DITK. It must either be a DUTK, a DCTK, or a DDTK. It cannot go out with a DITK simply because a DITK is known. The DITK must be handled securely with respect to the principles of dual control and split knowledge. In other words, you should have two people in the company, each knowing half of the DITK, and they enter each of their halves separately into the secure module. So nobody knows the full DITK. Manufacturing commands. Each DITK is split into components that I've already mentioned. Each component is entrusted to a different custodian. And please note that this is the only key in the STS domain that is in clear text. In other words, it's readable text. For this reason, it is imperative that it is handled according to the rules set out in the document, and that meters are never sent out of the factory environment encoded with the DITK. If they are, it means that people can change it from a DITK, if they know the DITK, to any key they like simply using the simulator. The ROM key is loaded into the HSM one component at a time using a special key entry device connected to a serial port on the security module by each key custodian. That gives you a little bit of security since if you have two key custodians, none of them should know the other's key part or key section, so none of them should know the full key. Still on the manufacturing commands, you have a generate and display key components, SMMG. Generates the DITK components and displays them on the key component entry device connected to the HSM CSP, critical security parameter port. The key components are generated such that combining all the components using exclusive ORs will yield the DITK. So you can ask the HSM to generate the key components, two of them, then they are exclusive ORed together and inserted, and the DITK is made up of those and stored into the security module. Load dispenser ROM key, SMML. That loads the dispenser ROM key into the ROM key slot. The DITK is entered in the form of components using that KECED device. Okay. The length of each key component is determined by the algorithm. So for EAS 7, obviously it's 16 bytes of data. Query dispenser ROM key slot, SMMQ. Load the dispenser ROM key into the ROM key slot. The DITK is entered in the form of components, we've said already. Returns STS CSP record empty if no DITK is loaded for the specific EA that you've chosen. Generating a manufacturer key change token. This constructs a set of tokens using the ROM key. So in other words, you're going from DITK to either a DDTK, DUTK, or DCTK. And in the production environment, this is what will happen. Once you've manufactured meters, they'll all be in a DITK mode. And right at the end, before you put them into storage or ship them to the customer, they go from DITK to one of the other keys. The key change rules previously shown do not apply to a manufacturing key change token set. The HSM, however, ensures that the destination VK is not expired. The SMMK never sets a rollover bit in the key change token, but will work with a VK of any base state value. From time to time, you'll see what we call a KCV or key check value associated with the key. Well, these key check value algorithms differ depending on which key we're talking about and which key length. Key check values are meant to assist in identifying a key, contributing to confidence that the expected key material is present. This identification is probabilistic, it's not unique. Because the KCV is a lot shorter than the key, you could still theoretically get the correct KCV value for a different key. And it does not contribute to the security of a key management, of key management. There are two KCV algorithms used in the STS domain: a DES KCV for 64-bit keys and a SHA-256 KCV for 128-bit keys. So the DES algorithm says encrypt a 0 block, so that's 8 bytes of all 0, with the key that you're trying to get the KCV for. Take the leftmost 3 bytes of the result as the check value. That's your KCV value. In the SHA-256 algorithm, you concatenate the byte 01 with the key in that order. So it'll be key and then 01. Compute the SHA-256 hash of this concatenation and take the leftmost 3 bytes of the result as a check value. A final note: some features and command parameter ranges differ between HSM hardware platforms. The HSM hardware platform behavior also differs when an HSM is in a tampered state. The HSM may also support additional commands, including proprietary commands necessary for the production and maintenance of the security module. So those commands are not provided in the standard because obviously they are proprietary to the manufacturer. Please refer to the manuals supplied by the manufacturer if you want to find out if there are other commands that you may use. In the next video, we'll look at some examples of these commands and responses. This brings us to the end of this part of the video series. I hope you found this video helpful, and I hope to see you for the rest of the video series. Goodbye and see you again soon.